Okay, next we have moments. So a moment is a situation in physics and engineering where it is when you have a force that has a turning effect around a pivot point. So a moment can be a single force around a pivot point, or a moment can occur when you have forces in equal and opposite directions, but are in line with each other. So again, moment is when we're dealing with stuff that's rotating. We have an example over here that we have a spanner. If you have a spanner going around a bolt, you have the situation where you're putting force onto the spanner and you are rotating the spanner around that particular bolt. The formula that we use for a moment is moment equals force times distance, and it's perpendicular distance, but we'll get to that later. So for the first example we have over there with the spanner, we have our force is the force we're putting down with our palm. The distance is the distance between the force and the nut that it's rotating, and that is producing a moment. Same thing we have there with that, I forgot what tool that is, but it's something that rotates. It makes it's a die for a thread. It makes threads. As it's rotating the die in the thread, you're producing a force on the left and right side. If you imagine if you're turning something like a bike handle, it could be the same thing. You're putting a force up and down, but the force you have in it has a distance, and that is producing a moment. If you click this link over here that I have listed in the bottom of the PowerPoint, it should send you to some helpful resources on that. So let's go on to the next one. So the example we have here, we're going to calculate the moment on this spanner if D is equal to 25 centimeters and the force applied is 25. So we said we know our formula is moments equals force times distance. Our force is equal to 25. That's already given. So our force is 25, so that's given. And we know that it is at 25 centimeters. So we said our equation is force times distance. We are using the SI units for here. So our force is measured in newtons, and our distance is measured in meters. So 25 centimeters is 0.25. It's not 25, it's 0.25 or 0.25 because it is 0.25 of a meter. 25 times 0.25 is 6.25. And there we have our units. We have Nm, which is Newton meters, which makes sense because our original forces is newtons and meters. Okay. Now in the same way that we can add up our forces by just putting them head to tail or graphically adding up the sum of all the forces, we do the same thing with moments. We can add up the sum of all the moments. So we do this by finding the individual moment caused by each external force on our system. So over here we have a massive spanner with two students trying to pull it down. We can say this first student is producing a force down and it's at a distance 1 and a force 1. So our total moment is this is our moment 1. And that is force 1 times distance 1. And this over here is our moment 2, which is our force 2 times distance 2. We want to define clockwise as positive and counterclockwise as negative in the same way as when we were doing our resultant forces. We were saying how up was positive and down was negative. We have to do that in the same sense with our moments. The next thing that gets students a bit confused about moments is moments only care about perpendicular distance. We saw before that our equation for our moments was moments equals force times distance, but this over here is our perpendicular distance. Right, it's our perpendicular distance. So over here we have two examples. We have this could be just like a lever or something like a switch, and we have over here we have our blue forces. So in this case over here, I'm going to say that the handle is 1 length long in each case, right? So over here, you're producing a force that is going directly down the whole time. What's happening is as I said, the force only cares about the perpendicular distance. If we were to zoom in onto this case over here, right? Let's zoom in. We have a a large thing over here. If we are pushing down with this force over here, it only cares about perpendicular distance, which means if we were to draw a line going vertically down, and sorry, if we imagine our force is an infinitely long line, we want to find out the point where it is at perpendicular, so a right angle to the place that it's rotating about. So, and this is the actual length that you want. This is the length. This is not the length. I see the problem that I did X for both of them, but we don't want this length over here. So we don't want to get confused with this length. We actually want this length over here connected to the X. So, and these situations, this looks similar in this case, but over here we see the force is actually at a right angle the whole time. So these are going to produce different moments. Let's oops. So we can see the difference with these. We'll do it by example. So let's look at the difference. So the difference is we have two forces. We have one force over here. So this over here is going to be 45 degrees, and this over here is also going to be 45 degrees. And we're going to say this one over here is this length over here. We'll say this length is 1 meter. This length over here is 1 meter. Our force over here is going vertically down, and let's just say it's a 5 Newton force. And this one over here is at a perpendicular angle, so it is 5 newtons. We can find the moments. This one over here should be the easy one, so let's just do that one first. We know this moment over here, about this point, our moment is going to be equal force times distance. Our force is 5 newtons times a distance of 1, so its moment is 5 Newton meters. Okay, that's easy. This one over here, our perpendicular distance is not 1, because if we were to draw an infinitely long line, if we were to draw an infinitely long line, oh boy. If we draw an infinitely long line through the page, we see that it actually becomes a right angle, right, at this point over here. So this is turning into our right angled triangle problem. So our distance is actually this distance over here, which is, this distance over here is, we can find it out with our sine rule. So that's cos actually. So cos 45 equals whatever distance that is. So let's just call that distance x over 1. So we're saying our x is going to equal 1 times cos 45. So it's actually going to equal, x is going to equal 0.707. So our moment for this one over here, moment equals force times distance, is going to equal 1 times 0.70, so sorry, not 1, 5. 5 times 0.707, so it's going to equal 3.5. So we can see here, this is the difference. If we have it at perpendicular, we get a 5 newtons. If we get it at 3.5, we get, sorry, if we get it at 45 degrees, it's at 3.5 Newton meters. So the question I'm going to ask you, what happens if we get to a point where the force is pointing into the area of rotation? So what if our force over here is actually moving like this? Right, and I'm gonna let you think about that question. Okay, so we have force and moments. So we're just going to do a bit of an example here of what each one of these could be used for. We know that forces are used, what type of movement do? They do translational. So forces will move an object in a straight line. You imagine you have an object, you have a block, and you push it, it's going to move in a straight direction. While moments is going to work via rotation. So if you want something to spin, rotate it, the point is going to go around a single point. How this impacts the body, we have our force for, it's based off inertia, and we have our force equals mass times acceleration. We've seen that formula before. And moments uses a moment of inertia, which is our moment equals the moment of inertia times the angular acceleration. Now you don't have to worry about what those words mean. I want you to know that there is an equivalent in the force equals mass times acceleration for our rotation. And it makes sense in a way. If you have an object and you want it to spin faster, which is our angular acceleration, you can put more of a moment into it. So if you want to make a motor spin, if you want your car wheels to spin faster, you've got to put more of a moment in you have to get your engine to produce more of a moment. The other option is you can also change your moment of inertia, which is it's a value based off the weight of the system, how close it is to the center. If you've seen ice skaters, when they want to spin really fast, they bring their body up really skinny, and so their mass is very close towards the center, so they can spin really fast. And when they want to slow down, they stick their arms out to slow down their rate of spinning. Then we have how is this measured? So these are just the units that we typically use. When we deal with how our body moves due to forces, we have displacement, velocity, and acceleration. When we have our for rotation stuff, we have angular displacement, we have angular velocity, and we have angular acceleration. Now, unlike in our forces where we have meters per second, and meters per second per second, when we come to angular displacement, when it's used in formulas, we usually use radian. So radians per second, per second. But radians just is a difficult one to write down on questions. So we also like to use degrees, usually when we're like describing a question. But also, it's not that difficult to convert degrees to radians. We know how to do that. So just something to keep an eye on for that.